Good day, everyone. My name is Reifel del VILLAR,
And I am Genesis Cruz.
and we will present our thesis study entitled Design of an Arduino-powered sleep monitoring system based on electroocculography or EOG with temperature control applications.
The main objective of our thesis study is to design an Arduino-based electroocculogram sleep monitoring system with an application in temperature control. Shown are our other objectives. Due to the COVID-19 restrictions and limitations, the testing for the prototype was conducted to 10 users without diagnosed chronic conditions. The inclusion criteria were that the participants are adults of 18 to 25 years old.
This is the block diagram for the entire prototype. The EOG signals would come from the AD8232 sensor via the Arduino Uno. Meanwhile, the temperature control system consists of the DHT22 sensor that is connected to the Arduino Mega module, which would relay the signal from the computer to the air conditioner. Meanwhile, this is the actual prototype, and we can see the two Arduino modules inside. The box also has holes in order to fit the wires through. Meanwhile, this is the placement of the electrodes on the user. For the sleep stage determination, three steps would be done with the EOG design. First is pre-processing, where the EOG signal would be picked up by the AD8232 module. Next, this is the schematic diagram for the EOG design. The electrodes are attached to the AD8232 component, and the Arduino Uno module would pick up the analog output from the sensor. So in the next slide, after pre-processing, the filtered signal would then undergo feature extraction. And for this study, two algorithms were used, which are MSE and AR modeling. Lastly, the features would go through the sleep stage classification, and the linear discriminant analysis or LDA algorithm would be used. Data from Fitbit would be used for validation.
The program also contains an algorithm that would determine whether the room temperature would be adjusted based on the determined sleep stage and measured temperature from the DHT22 component. A briefing was held before the data collection phase to ensure that the users were well oriented. The room was 21 square meters and the air conditioning unit is 1 horsepower. For the testing, the room was airtight and the users were tested in good weather conditions only.
The performance of the EOG design was compared with the Fitbit sleep tracker, which was worn by the users together with the EOG. Here is the hypnogram of user 1 during the first night, where the blue line represents the EOG design, while the orange line represents the Fitbit sleep stages. According to the confusion matrix, the overall accuracy is 82.31%, which means that the EOG design has a substantial agreement with the commercially available sleep tracker, Fitbit. Meanwhile, this table sums up the accuracy of the design for each user. This means that the performance of the EOG design does not vary too much between the users.
The experimental setup was done and the temperature measurement was recorded with suitable display in the MATLAB GUI. The tests and observations are presented in the figures. The orange line represents the set point temperature, while the blue line represents the recorded temperature through the DHT22 sensor. These are the temperature variations for the rest of the users. The table shows the standard error obtained from the data, which is 3.81%. The range confidence interval between the values gives a 0.5% relative hazard, while the range prediction interval has a 7.3% relative hazard. This indicates a good level of precision of the temperature control system. The Arduino holds variables at a set value. These are the two variables required, the actual input signal and the desired set point value. Once the temperature is known, it is compared with the set point value. There corresponds a temperature adjustment for each sleep stage read from the EOG devices.
The questionnaire was evaluated for each user regarding their sleep on both nights, and the results are shown as follows. These results show that users had less difficulty sleeping and felt more refreshed when the temperature control system was added. So in conclusion, the researchers have designed a functioning Arduino-based electroocculogram or EOG sleep monitoring system with an application in thermal environment control. The Arduino-based EOG design can classify 4 different sleep stages, and it has an overall accuracy of 82.31%. The temperature control system has a standard error of 3.8%, and it can adjust into 4 different temperatures, 26, 27, 28, and 29 degrees Celsius. So in the next slide, The EOG design was also successful with combining the temperature control system and the user's sleep were assessed for both nights. From the results, we can see that the users had less difficulty sleeping on the second night and woke up less often. So for the recommendations, the students recommend increasing the number of participants as well as including a group of participants with sleeping problems in order to evaluate whether the sleep has improved. Next is to integrate the EOG design into a wireless sleep mask as well as a mobile application for displaying sleep log. This concludes our presentation.